Part 1 Basic Analysis. Chapter 1 Basic Static Techniques. We begin our exploration of malware analysis, which is static analysis, which is usually the first step in studying malware. Static analysis describes the process of analyzing the code or structure of a program to determine its function. The program itself is not run at this time. In contrast, when performing dynamic analysis, the analyst actually runs the program, as you'll learn in Chapter 3. This chapter discusses multiple ways to extract useful information from executables. In this chapter, we'll discuss the following techniques: using antivirus tools to confirm maliciousness, using hashes to identify malware, gleaning information from a file's strings, functions, and headers. Each technique can provide different information, and the ones you use depend on your goals. Typically, you'll use several techniques to gather as much information as possible. Antivirus scanning, a useful first step. When first analyzing prospective malware, a good first step is to run it through multiple antivirus programs, which may already have identified. But antivirus tools are certainly not perfect. They rely mainly on a database or of identifiable pieces of known suspicious code, file signatures, as well as behavioral and pattern matching analysis, heuristics, to identify suspect files. One problem is that malware writers can easily modify their code, thereby changing the program signature and evading virus scanners. Also, rare malware often goes undetected by antivirus software because it's simply not in the database. Finally, heuristics, while often successful in identifying unknown malicious code, can't be bypassed by new and unique malware. Because various antivirus programs use different signatures and heuristics, it's useful to run several different antivirus programs against the same piece of suspected malware. Websites such as virustotal.com allow you to upload a file for scanning by multiple antivirus programs. Engines. VirusTotal generates a report that provides the total number of engines that mark the file as malicious, the malware name, and, if available, additional information about the malware. Hashing, a fingerprint for malware. Hashing is a common method used to uniquely identify malware. The malicious software is run through a hashing program that produces a unique hash that identifies that malware, a sort of fingerprint. The message digest algorithm 5, MD5 hash function is the one most commonly used for malware analysis, though the secure hash algorithm 1, SHA-1, is also popular. For example, using the freely available MD5 deep program to calculate the hash of the solitaire program that comes with Windows would generate the following output. The hash is the GUI-based WinMD5 calculator, shown in figure 1.1, can calculate and display hashes for several files at a time. Once you have a unique hash for a piece of malware, you can use it as follows. Use the hash as a label. Share the hash with other analysts to help them to identify malware. Search for the hash online to see if the file has already been identified. Figure 1.1 Output of WinMD5. Finding strings. A string in a program is a sequence of characters such as the. The program contains strings if it prints a message, connects to a URL, or copies a file to a specific location. Searching through the strings can be a simple way to get hints about the functionality of a program. For example, if a program accesses a URL, then you will see the URL access stored as a string in the program. You can use the strings program bit.ly/ic4pll to search an executable for strings, which are typically stored in either ASCII or Unicode format. Note: Microsoft uses the term wide character string to describe its implementation of Unicode strings, which varies slightly from the Unicode standards. Throughout this book, when we refer to Unicode, we are referring to the Microsoft implementation. Both ASCII and Unicode formats store characters in sequences that end with a null terminator to indicate that the string is complete. ASCII strings use 1 byte per character, and Unicode uses 2 bytes per character. Figure 1-2 shows the string BAD stored as ASCII. The ASCII string is stored as the bytes 0x42, 0x41, 0x44, and 0x00, where 0x42 is the ASCII representation of a capital letter B, 0x41 represents the letter A, and so on. The 0x00 at the end is a null terminator. Figure 1.2, ASCII representation of the string bad. Figure 1.3 shows the string bad stored as Unicode. The Unicode string is stored as the bytes 0x42, 0x00, 0x41, and so on. A capital B is represented by the bytes 0x42 and 0x00, and the null terminator is 2 0x00 bytes in a row. Figure 1-3, Unicode representation of the string bad. When string searches an executable for ASCII and Unicode strings, it ignores context and formatting, so it can analyze any file type and detect strings across an entire file, though this also means that it may identify bytes of characters as strings when they are not. String searches for a 3-letter or greater sequence of ASCII and Unicode characters, followed by a string termination character. Sometimes the strings detected by the strings program are not actual strings. For example, if strings finds the sequence of bytes 0x56, 0x50, 0x33, and 0x00, it will interpret that as the string VP3. But those bytes may not actually represent that string. They could be a memory address, CPU instructions, or data used by the program. Strings leaves it up to the user to filter out the invalid strings. Fortunately, most invalid strings are obvious because they do not represent legitimate text. For example, the following excerpt shows the result of running strings against the file bp6.ex_. In this example, the bold strings can be ignored. Typically, if a string is short that doesn't correspond to words, it's probably meaningless. On the other hand, the strings get layout at 1 and set layout at 2 are Windows functions used by the Windows graphics library. We can easily identify these as meaningful strings because Windows function names normally begin with a capital letter and subsequent words also begin with a capital letter. GDI32.dll at 3 is meaningful because it's the name of a common Windows dynamic link library, DLL, used by graphics programs. DLL files contain executable code that is shared among multiple applications. As you might imagine, the number 99.124.22.1 at 4 is an IP address, most likely one that the malware will use in some fashion. Finally, at 5, mail system DLL is invalid. Sent mail failed to send message is an error message. Often, the most useful information obtained by running strings is found in error messages. This particular message reveals 2 things. The subject malware sends messages, probably through email, and it depends on a mail system DLL. This information suggests that we might want to check email logs for suspicious traffic, and that another DLL, mail system DLL, might be associated with this particular malware. Note that the missing DLL itself is not necessarily malicious. Malware often uses legitimate libraries and DLLs to further its goals. Packed and obfuscated malware. Malware writers often use packing or obfuscation to make their files more difficult to detect or analyze. Obfuscated programs are ones whose execution the malware author has attempted to hide. Packed programs are a subset of obfuscated programs in which the malicious program is compressed and cannot be analyzed. Both techniques will severely limit your attempts to statically analyze the malware. Legitimate programs almost always include many strings. Malware that is packed or obfuscated contains very few strings. If upon searching a program with strings, you find that it has only a few strings, it is probably either obfuscated or packed, suggesting that it may be malicious. You'll likely need to throw more than static analysis at it in order to investigate further. Note: packed and obfuscated code will often include at least the functions load library and get proc address, which are used to load and gain access to additional functions. Packing files. When the packed program is run, a small wrapper program also runs to decompress the packed file and then run the unpacked file, as shown in Figure 1.4. When a packed program is analyzed statically, only the small wrapper program can be dissected. Chapter 18 discusses packing and unpacking in more detail. Figure 1.4. The file on the left is the original executable, with all strings, import, and other information visible. On the right is a packed executable. All of the packed file's strings, imports, and other information are compressed and invisible to most static analysis tools. Detecting packets with PEID. One way to detect packed files is with the PEID program. You can use PEID to detect the type of packer or compiler employed to build an application, which makes analyzing the packed file much easier. Figure 1.5 shows information about the ORIG_AF2.ex_ files reported by PEID. Figure 1.5, the PEID program. Note: development and support for PEID has been discontinued since April 2011, but it's still the best tool available for packer and compiler detection. In many cases, it will also identify which packer was used to pack the file. As you can see, PEID has identified the file as being packed with UPX version 0.89.6-1.02 or 1.05-2.90. Just ignore the other information shown here for now. We'll examine this program in more detail in Chapter 18. When a program is packed, you must unpack it in order to be able to perform any analysis. The unpacking process is often complex and is covered in detail in Chapter 18, but the UPX packing program is so popular and easy to use for unpacking that it deserves special mention here. For example, to unpack malware packed with UPX, you would simply download UPX, upx.sourceforge.net, and run it like so, using the packed program as input. upx-d packedprogram.exe. Note: many PEID plugins will run the malware executable without warning. See Chapter 2 to learn how to set up a safe environment for running malware. Also, like all programs, especially those used for malware analysis, PEID can be subject to vulnerabilities. For example, PEID version 0.92 contained a buffer overflow that allowed an attacker to execute arbitrary code. This would have allowed a clever malware writer to write a program to exploit the malware analyst's machine. Be sure to use the latest version of PEID. Portable executable file format. So far, we have discussed tools that scan executables without regard to their format. However, the format of a file can reveal a lot about the program's functionality. The portable executable file format is used by Windows executables, object code, and DLLs. The PE file format is a data structure that contains the information necessary for the Windows OS loader to manage the wrapped executable code. Nearly every file with executable code that is loaded by Windows is in the PE file format, though some legacy file formats do appear on rare occasion in malware. PE files begin with a header that includes information about the code, the type of application, required library functions, and space requirements. The information in the PE header is of great value to the malware analyst. Linked libraries and functions. One of the most useful pieces of information that we can gather about an executable file about an executable is the list of functions that import. Imports are functions used by one program that are actually stored in a different program, such as code libraries that contain functionality common to many programs. Code libraries can be connected to the main executable by linking. Programmers link imports to their programs so that they don't need to re-implement certain functionality in multiple programs. Code libraries can be linked statically at runtime or dynamically. Knowing how the library code is linked is critical to understanding of malware because the information you can find in the PE file header depends on how the library code has been linked. We'll discuss several tools for viewing an executable's imported functions in this section. Static, runtime, and dynamic linking. Static linking is the least commonly used method of linking libraries, although it is common in Unix and Linux programs. When a library is statically linked to an executable, all code from that library is copied into the executable, which makes the executable grow in size. When analyzing code, it's difficult to differentiate between statically linked code and the executable's own code, because nothing in the PE file header indicates that the file contains linked code. While on popular and friendly programs, runtime linking is commonly used in malware, especially when it's packed or obfuscated. Executables that use runtime linking connect to libraries only when that function is needed, not at program start, as with dynamically linked programs. Several Microsoft Windows functions allow programmers to import linked functions not listed in a program's file header. Of these, the two most commonly used are load library and getProc address. LDR getProc address and LDR load DLL are also used. Load library and getProc address allow a program to access any function in any library on the system, which means that when these functions are used, you can't tell statically which functions are being linked to by the suspect program. Of all linking methods, dynamic linking is the most common and the most interesting for malware analysts. When libraries are dynamically linked, the host OS searches for the necessary libraries when the program is loaded. When the program calls the linked library function, that function executes within the library. The PE file header stores information about every library that will be loaded and every function that will be used by the program. The library is used and functions called are often the most important part of the program, and identifying them is particularly important because it allows us to guess at what the program does. For example, if a program imports the function URL download to file, you might guess that it connects to the internet to download some content and it then stores in a local file. Exploring dynamically linked functions with Dependency Walker. The Dependency Walker program, dependenzywalker.com, distributed with some versions of the Microsoft Visual Studio and other Microsoft development packages, lists only dynamically linked functions in an executable. Figure 1.6 shows the dependency walkers analysis of services.ex_. 1. The file left pane at 2 shows the program as well as the DLLs being imported, namely kernel32.dll and ws2_32.dll. Figure 1.6, the dependency walker program. Clicking kernel32.dll shows its imported functions in the upper right pane at 3. We see several functions, but the most interesting is create process A, which tells us that the program will probably create another process and suggests that when running the program we should watch for the launch of additional programs. The middle right pane at 4 lists all functions in kernel32.dll that can be imported, information that is not particularly useful to us. Notice the column in panes 3 and 4 labeled ordinal. Executables can import functions by ordinal instead of name. When importing a function by ordinal, the name of the function never appears in the original executable, and it can be harder for an analyst to figure out which function is being used. When malware imports a function by ordinal, you can find out which function is being imported by looking up the ordinal value in the pane at 4. The bottom two panes, 5 and 6, list additional information about the versions of DLLs that would be loaded if you run the program and any reported errors respectively. A program's DLL can tell you a lot about its functionality. For example, the table 1.1 lists common DLLs and what they tell you about the application. Table 1.1 common DLLs. DLL description. kernel32.dll. This is a very common DLL that contains core functionality such as access and manipulation of memory, files and hardware. At varp32.dll, this DLL provides access to advanced core Windows components such as the Service Manager and Registry. User32.dll. This DLL contains all the user interface components such as buttons, scroll bars, and components for controlling and responding to user actions. GDI32.dll. This DLL contains functions for displaying and manipulating graphics. NTDLL.dll. This DLL is the interface to the Windows kernel. Executables generally do not import this file directly, although it is always imported indirectly by kernel32.dll. If an executable imports this file, it means that the author intended to use functionality not normally available to Windows programs. Some tasks, such as hiding functionality or manipulating processes, will use this interface. wsoc32.dll and ws2_32.dll. These are networking DLLs. A program that accesses either of these most likely connects to a network or performs network-related tasks. Winning.dll. This DLL contains higher-level networking functions that implement protocols such as FTP, HTTP, and NTP. Function naming conventions. When evaluating unfamiliar Windows functions, a few naming conventions are worth noting because they come up often and might confuse you if you don't recognize them. For example, you will often encounter function names with an X suffix, such as create Windows X. When Microsoft updates a function and the new function is incompatible with the old one, Microsoft continues to support the old function. The new function is given the same name as the old function with an added EX suffix. Functions that have been significantly updated twice have two EX suffixes in their names. Many functions that take strings as parameters include an A or a W at the end of their names, such as create directory W. This letter does not appear in the documentation for the function. It simply indicates that the function accepts a string parameter and that there are two different versions of the function, one for ASCII strings and one for wide character strings. Remember to drop the trailing A or W when searching for the function in the Microsoft documentation. Imported functions. The PE file header also includes information about specific functions used by an executable. The names of these Windows functions can give you a good idea about what the executable does. Microsoft does an excellent job of documenting the Windows API through the Microsoft Developer Network MSDN library. You'll also find a list of functions commonly used by malware in Appendix A. Exported functions. Like imports, DLLs, and EXEs, export functions to interact with other programs and code. Typically, a DLL implements one or more functions and exports them for use by an executable that can then import and use them. The PE file contains information about which functions a file exports. Because DLLs are specifically implemented to provide functionality used by EXEs, exported functions are most common in DLLs. EXEs are not designed to provide functionality for other EXEs, and exported functions are rare. If you discover exports in an executable, they often will provide useful information. In many cases, software authors name the exported functions in a way that provides useful information. One common convention is to use the name used in the Microsoft documentation. For example, in order to run a program as a service, you must first define a service main function. The presence of an exported function called service main tells you that the malware runs as part of a service. Unfortunately, while the Microsoft documentation calls the function service main, and it's common for programmers to do the same, the function can have any name. Therefore, the names of exported functions are actually of limited use against sophisticated malware. If malware uses exports, it will often either omit names entirely or use unclear or misleading names. You can view export information using the dependency walker program discussed in exploring dynamically linked functions with dependency walker. For a list of exported functions, click the name of the file you want to examine. Referring back to Figure 1.6, Window 4 shows all of a file's exported functions. Static analysis in practice. Now that you understand the basics of static analysis, let's examine some real malware. We'll look at the potential keylogger and then a packed program. Potential keylogger.exe, a non-packed executable. Table 1.2 shows an abridged list of functions imported by potential keylogger.exe as collected using dependency walker. Because we see so many imports, we can immediately conclude that the file is not packed. Table 1.2, an abridged list of DLLs and functions imported from potential keylogger.exe. kernel32.dll, user32.dll, user32.dll continued. Like most average-sized programs, this executable contains a large number of imported functions. Unfortunately, only a small minority of those functions are particularly interesting for malware analysis. Throughout this book, we will cover the imports for malicious software, focusing on the most interesting functions from a malware analysis standpoint. When you are not sure what a function does, you will need to look it up. To help guide your analysis, Appendix A lists many other functions of greatest interest to malware analysts. If a function is not listed in Appendix A, search for it on MSDN online. As a new analyst, you will spend time looking up many functions that aren't very interesting, but you'll quickly settle out which functions could be important and which ones are not. For the purposes of this example, we will show you a large number of imports that are uninteresting, so you can become familiar with looking at a lot of data and focusing on some key nuggets of information. Normally, we wouldn't know that this malware is a potential keylogger, and we would need to look for functions that provide the clues. We will be focusing on only the functions that provide hints to the functionality of the program. The inputs for kernel32.dll on table 1.2 tells us that this software can open and manipulate processes such as open process, get current process, and get process heap, and files such as read file, create file, and write file. The functions find first file and find next file are particularly interesting ones that we can use to search through directories. The inputs from user32.dll are even more interesting. The large number of GUI manipulation functions such as register class X, set window text, and show window indicates a high likelihood that this program has a GUI, though the GUI is not necessarily displayed to the user. The function set windows hookx is commonly used in spyware and is the most popular way that keyloggers receive keyboard inputs. This function has some legitimate uses, but if you suspect malware and you see this function, you're probably looking at keylogging functionality. The function register hotkey is also interesting. It registers a hotkey such as Ctrl-Shift-P, so that whenever the user presses that hotkey combination, the application is notified. No matter which application is currently active, a hotkey will bring up the user to this application. The inputs from GDI32.dll are graphics related and simply confirm that the program probably has a graphical user interface. The inputs from shell32.dll tells us that this program can launch auto programs, a feature common to both malware and legitimate programs. The imports from advarp32.dll tell us that this program uses the registry, which in turn tells us that we should search for strings that look like registry keys. Registry strings look a lot like directories. In this case, we found the string software Microsoft Windows current version run, which is a registry key commonly used by malware that controls which programs automatically run when Windows starts up. This executable also has several exports: low-level keyboard proc and low-level mouse proc. Microsoft Communication says the low-level keyboard proc hook procedure is an application-defined or library-defined callback function used with the set Windows hookx function. In other words, this function is used with set Windows hookx to specify which function will be called when a specified event occurs. In this case, the low-level keyboard event. The documentation for set Windows hookx further explains that this function will be called when certain low-level keyboard events occur. The Microsoft documentation uses the same low-level keyboard proc, and the programmer in this case did as well. We were able to get valuable information because the programmer didn't obscure the name of an export. Using the information gleaned from a static analysis of these imports and exports, we can draw some significant conclusions or formulate some hypotheses about this malware. For one, it seems likely that this is a local keylogger that uses set Windows hookx to record keystrokes. We can also surmise that it has a GUI that is displayed only to a specific user, and that the hotkey registered hotkey specifies the hotkey that the malicious user enters to see the keylogger GUI and access recorded keystrokes. We can further speculate from the registry function and the existence of software Microsoft Windows current version run that this program sets itself to load at system startup. Packed program.exe, a dead end. Table 1.3 shows a complete list of the functions imported by a second piece of known malware. The brief T of this list tells that this program is packed or obfuscated, which is further confirmed by the fact that this program has no readable strings. A Windows compiler would not create a program that imports such a small number of functions. Even a hello world program would have more. Table 1.3 DLLs and functions imported from packed program.exe. Kernel 32.dll, user 32.dll. Get module handle A, message box A, load library A. Get proc address, exit process, virtual alloc, virtual free. The fact that this program is packed is a valuable piece of information, but its packed nature also prevents us from learning anything more than the program using basic static analysis. We'll need to try more advanced analysis techniques such as dynamic analysis covered in Chapter 3 or unpacking covered in Chapter 18. The PE file headers and sections. PE file headers can provide considerably more information than just import. The PE file format contains a header followed by a series of sections. The header contains metadata about the file itself. Following the header are the actual sections of the file, each of which contains useful information. As we progress through the book, we will continue to discuss strategies for viewing the information in each of these sections. The following are the most common and interesting sections in the PE file. .text. The .text section contains the instructions that the CPU executes. All other sections store data and supporting information. Generally, this is the only section that can execute, and it should be the only section that includes code. .rdata. The .rdata section typically contains the import and export information, which is the same information available from both dependency walk and PEV. This section can also store other read-only data used by the program. Sometimes a file will contain an .idata and .edata section which store the import and export information. See Table 1.4. .data. The .data section contains the program's global data, which is accessible from anywhere in the program. Local data is not stored in this section or anywhere else in the file. We addressed this topic in Chapter 6. .rsrc. The .rsrc section includes the resources used by the executable that are not considered part of the executable, such as icons, images, menus, and strings. Strings can be stored either in the .rsrc section or in the main program, but they're often stored in the rsrc section for multi-language support. Section names are often consistent across a compiler but can vary across different compilers. For example, Visual Studio uses .text for executable code, but Ball and Delphi uses code. Windows doesn't care about the actual name, since it uses all the information in the PE header to determine how a section is used. Furthermore, the section names are sometimes obfuscated to make analysis more difficult. Luckily, the default names are used most of the time. Table 1.4 lists the most common you'll encounter. Table 1.4 sections of a PE file for Windows executable. Executable description. .text contains the executable code. .rdata holds read-only data that is globally accessible within the program. .data stores global data accessed throughout the program. .idata sometimes present and stores the import function information. If this section is not present, the import function information is stored in the .rdata section. .edata sometimes present and stores the export function information. If this section is not present, the export function information is stored in the rdata section. .pdata present only in 64-bit executables and stores exception handling information. .rsrc stores resources needed by the executable. .reloc contains information for relocation of library files. Examining PE files with PE view. The PE file format stores interesting information within its header. We can use the PE view tool to browse through the information as shown in figure 1.7. In the figure, the left pane at 1 displays the main parts of a PE header. The image file header entry is highlighted because it is currently selected. The first two parts of the PE header, the image DOS header and the mdtos stub program, are historical and often no information of particular interest to us. The next section of the PE header, image NT headers, shows the NT headers. The signature is always the same and can be ignored. The image file header entry, highlighted and displayed in the right panel at 2, contains basic information about the file. The time and date stamp description at 3 tells us when this executable was compiled, which can be very useful in malware analysis and incident response. For example, an old compile time suggests that this is an older attack, and antivirus programs might contain signatures for the malware. A new compile time suggests the reverse. Figure 1.7, viewing the image file header in the PE view program. That said, the compile time is a bit problematic. All Delphi programs use a compile time of June 19, 1992. If you see that compile time, you're probably looking at a Delphi program and you won't really know when it was compiled. In addition, a competent malware writer can easily fake the compile time. If you see a compile time that makes no sense, it probably was faked. The image optional header section includes several important pieces of information. The subsystem description indicates whether this is a console or GUI program. Console programs have the value image subsystem Windows GUI and run inside a command window. GUI programs have the value image subsystem Windows GUI and run within the Windows system. Less common subsystems such as Native or Xbox are also used. The most interesting information comes from the section headers, which are in image section header, as shown in figure 1.8. These headers are used to describe each section of a PE file. The compiler generally creates and names the sections of an executable, and the user has little control over these names. As a result, the sections are usually consistent from executable to executable, see table 1.4, and any deviations may be suspicious. For example, in figure 1.8, vector size at 1 tells us how much space is allocated for a section during the loading process. The size of raw data at 2 shows how big the section is on disk. These two values should usually be equal, because data should take up just as much space on the disk as it does in memory. Small differences are normal, and are due to differences between alignment in memory and on disk. The section sizes can be useful in detecting packed executables. For example, if the virtual size is much larger than the size of raw data, you know that the section takes up more space in memory than it does on disk. This is often indicative of packed code, particularly if the .text section is larger in memory than on disk. Figure 1.8, viewing the image section header .text section in the PE view program. Table 1.5 shows the sections from potential keylogger.exe. As you can see, the .text, .rdata, and .rsrc sections each has a virtual size and size of raw data value of about the same size. The .data section may seem suspicious because it has a much larger virtual size than raw data size, but this is normal for the .data section in Windows programs. But note that this information alone does not tell us that the program is not malicious. It simply shows that it is not likely not packed and that the PE file header was generated by a compiler. Table 1.5, section information for potential keylogger.exe. Section, virtual size, size of raw data. .text, 7AF5, 7COO. .data, 17A0, 0200. .rdata, 1AF5, 1C00, 1RSRC, 72B8, 7400. Table 1.6 shows the sections from packed program.exe. The sections in this file have a number of anomalies. The sections named digfpds, .sdfuk, and keygigl are unusual, and the .text, .data, and .rdata sections are suspicious. The .text section has a size of raw data value of 0, meaning that it takes up no space on disk, and its virtual size value is A000, which means that space will be allocated for the .text segment. This tells us that a packer will unpack the executable code to the allocated .text section. Table 1.6 section information from packed program.exe. Viewing the resource section with resource hacker. Now that we've finished looking at the header for the PE file, we can look at some of the sections. The only section we can examine without additional knowledge from later chapters is the resource section. You can use the free resource hacker tool found at angusj.com to browse the .rsrc section. When you click through the items in Resource Hacker, you'll see the strings, icons, and menus. The menus displayed are identical to what the program does, to what the program uses. Figure 1.9 shows the Resource Hacker display for the Windows calculator program, calc.exe. Figure 1.9, the Resource Hacker tool display for calc.exe. The panel on the left shows all resources included in this executable. Each root folder shown in the left pane at 1 stores a different type of resource. The informative sections for malware analysis include the icon section lists images shown when the executable is in a file listing. The menu section stores all menus that appear in various windows such as File, Edit, and View menus. This section contains the names of all the menus as well as the text shown for each. The name should give you a good idea of their functionality. The dialog section contains the program's dialog menus. The dialog at 2 shows what the user will see when running to calc.exe. If we knew nothing else about calc.exe, we could identify it as calculator program simply by looking at its dialog menu. The string table section stores strings. The version info section contains a version number and often the company name and a copyright statement. The .rsrc section shown in Figure 1.9 is typical of Windows applications and can include whatever a programmer requires. Note: malware and occasionally legitimate software often store an embedded program or driver here, and before the program runs, they extract the embedded executable or driver. Resource Hacker lets you extract these files for individual analysis. Using other PE file tools. Many other tools are available for browsing a PE header. Two of the most useful tools are PE Browse Professional and PE Explorer. PE Browse Professional is similar to PE View. It allows you to look at the bytes from each section and shows the parsed data. PE Browse Professional does the better job of presenting information from the resource.rsrc section. PE Explorer, heaventools.com, has a rich GUI that allows you to navigate through the various parts of the PE file. You can edit certain parts of the PE file, and its included resource editor is great for browsing and editing the file's resources. The tool's main drawback is that it is not free. PE Header Summary. The PE header contains useful information for the malware analyst, and we will continue to examine it in subsequent chapters. Table 1.7 reviews the key information that can be obtained from a PE header. Table 1.7 information in the PE header. Field information revealed. Import functions from other libraries that are used by malware. Export functions in the malware that are meant to be called by other programs or libraries. Time date stamp, time when the program is compiled. Sections, name of the sections in the file and their sizes on disk and in memory. Subsystem indicates whether the program is a command line or GUI application. Resources, strings, icons, menus, and other information included in the file. Conclusion. Using a suite of relatively simple tools, we can perform static analysis on malware to gain a certain amount of insight into its function. But static analysis is typically only the first step, and further analysis is usually necessary. The next step is setting up a safe environment so you can run the malware and perform basic dynamic analysis, as you'll see in the next two chapters. Labs. The purpose of the labs is to give you an opportunity to practice the skills taught in the chapter. In order to stimulate realistic malware analysis, you will be given little or no information about the program you're analyzing. Like all of the labs throughout this book, the basic static analysis lab files have been given generic names to simulate unknown malware, which typically use meaningless or misleading names. Each of the labs consists of a malicious file, a few questions, short answers to the questions, and a detailed analysis of the malware. The solutions of the labs are included in Appendix C. The labs include two sections of answers. The first section consists of short answers, which should be used if you did the lab yourself and just want to check your work.
The second section includes detailed explanations for you to follow along with our solution and learn how we found the answers to the questions posed in each lab. Lab.1. This lab uses the files lab01-01.exe and lab01-01.dll. Use the tools and techniques described in this chapter to gain information about the files and answer the questions below. Questions. 1. Upload the files to virustotal.com and view the report. Does either file match any existing antivirus signatures? 2. When were these files compiled? 3. Are there any indications that either of these files is packed or obfuscated? If so, what are these indicators? 4. Do any inputs hint at what this malware does? If so, which inputs are they? 5. Are there any other files of host-based indicators that you could look for on infected systems? 6. What network-based indicators could be used to find this malware on infected machines? 7. What would you guess is the purpose of these files? Lab 1-2. Analyze the file lab0102.exe. Questions. 1. Upload the lab01-02.exe file to virustotal.com. Does it match any existing antivirus definitions? 2. Are there any indications that this file is packed or obfuscated? If so, what are these indicators? If the file is packed, unpack it if possible. 3. Do any imports hint at this program's functionality? If so, which inputs are they and what do they tell you? 4. What host or network-based indicators could be used to identify this malware on infected machines? Lab 1-3. Analyze the file lab01-03.exe. Questions. 1. Upload lab101-03.exe file to virustotal.com. Does it match any existing antivirus definitions? 2. Are there any indications that this file is packed or obfuscated? If so, what are these indicators? If the file is packed, unpack it if possible. 3. Do any imports hint at this program's functionality? If so, which imports are they and what do they tell you? 4. What host or network-based indicators could be used to identify this malware on infected machines? Lab 1-4. Analyze the file lab0102.exe. Questions. 1. Upload the file lab01-02.exe file to virustotal.com. Does it match any existing antivirus definitions? Are there any indications that this file is packed or obfuscated? If so, what are these indicators? If the file is packed, unpack it if possible. 3. When was this program compiled? 4. Do any imports hint at this program's functionality? If so, which imports are they and what do they tell you? 5. What host or network-based indicators could be used to identify this malware on infected machines? 6. This file has one resource in the resource section. Use resource hacker to examine that resource and then use it to extract the resource. What can you learn from the resource?